So should we
Should what?
should we actually try to adjust the spreadsheet, or you just have it?
We'll do it later.
Okay.
Maybe everybody can put their session, the number in on their line.
Oh, sorry. I guess people can see the clock. So.
Oh, we actually timing it?
Well, maybe somebody should time it. I think when you when you do your PowerPoint thing, you can use the timer. You use the timer feature, because then it'll automatically time the talk. No, you have to enable editing. And that's
timing?
Yeah.
Okay.
What's this?
Okay, it's not campaign.
What is that?
Okay. Actually, I haven't come through single practice yet, so that's right.
That's the first thing you're going to tell the audience?
Okay. Good morning.
That sounds better.
So my name is Bonnie Chen. I'm a postdoc in Jeremy Gravis Group at University of Pittsburgh, and this work is in collaboration with the with the Chen-Bong Group at University of Wisconsin-Madison, and which they provide our samples. And also, I would acknowledge our funding source from the Army Research Office and the Air Force
Office of Scientific Research. You can say the ARO and AFOSR, which I don't think you need to say. You can just keep going.
So our sample, in this one, our sample is an oxide interface, which is the less aluminum unstrengthened tightening. And they are the interface are atomic smooth, and they are grown by PLD. And then as the oxide interface, the electron interaction operations are intense and leading to some novel phenomena, like the 2D electron gas, and also the 2D electron gas can be tuned by the baggage voltage to the metal intertransition region, and also it can be tuned by the thickness of the LAO. So there exists a critical thickness 3 unit cell above that interface is conducting, and a 3 unit cell or below that interface is insulating. Also, the interface is superconducting with a typical critical temperature about 200 millikelvin, and the interface is magnetic, although both LAO and SPO are non-magnetic. Also, both the magnetism and the superconductivity can be coexistent, and the interface has really a strong rush-wise interaction as function of the carrier density across the interface. And in our part, basically, so we invent conduct FM lithography technique, which we can create like 1D nanoscale structures at this interface. So here I'll show you how we create this nanostructures with this FM lithography. So I'll play a cartoon here. So starting with a CAD design, and this is the optical image of the FM lithography, and this is the FM topography image. So here we are write a nanowire by the design. So once you can see by applying a positive voltage to the tip. So once the tip reaches the second electrode, we have a nanowire associated with the conduction jump. And also we can apply a negative voltage to the tip and cut the wire. So here you'll see it's cutting the wire now, and when the tip cuts through the wire and the conductor drops sharply. And the width you categorize can be as small as 3 nanometers. So here we have summarized some advantage of these LS2 nanowires. First, it's very clean. It's similar to the moderation dose interface. So we don't have any chemical exposure. So chemically very clean. And this technique is really is very versatile. We can combine with the right cut and pulsing techniques, so we can make sophisticated nanostructures without all the complicated freedom techniques. And then this interface has the nanowire has a very strong spin-off interaction, magnetic and superconductivity. So this nanowire was predicted to hold for myelin fermions, since it has all the ingredients. And our motivation here is just is to check whether all the ingredients are maximized at the same condition, so we can really see myelin fermions. But before that, we just we want to study these.
Yeah. I mean, you're already halfway through your talk, and you're still on the motivation.
Oh, sorry. Okay. Yeah. So.
And this is, you're going all over the place. It's like you're trying to give an invited talk.
Mm-hmm. Okay.
And this is a 10-minute talk, so you need to skip all this stuff.
Mm-hmm. Yeah, I mean, I can be much faster actually in the previous.
No, it's not a matter of faster. It's a matter of like cutting out stuff that's not relevant. I don't even know what your talk is about. Basically, what I've seen right now, it looks like it's a 50-minute talk, and you're giving a whole big long introduction. Just talking faster isn't the solution. You're gonna downsize and you're gonna focus. You want to have like one message, and you have to ask yourself, what's the message that you want to get across in this talk? Okay, keep going. So here we use this technique to create those confined nanowire structure. So at room temperature, we first write the nanowires, then we can gently cut the wire to create two tunneling barriers here. And then we can write two side gates to control the junction, and a big side gate to control the chemical potential of the nanowire. And so this is a typical transport we get from lots of devices. They all wait. What's the title of your talk?
It's electron transport in confined nanowire.
Okay, so all right. I just want to make sure, because I thought. Okay.
So,
I mean,
this is all in the abstract.
all right.
So this is a typical transport data we have from this kind of device. It's being produced for multiple devices. So here it's showing the temperature is 50 millikelvin. So we have a superconductivity in the exists in this device, and also we see Coulomb blockage, which you'll see the Coulomb diamonds here, and the other part is manifest as the two-pair component, which I'll explain later. So here I'll show the temperature dependence. Okay, sorry, it didn't play here. And also, as we saw on the field to some magnitude, we will see some very clear interference pattern, which we attribute to the Fabio Pro interference. It exists at zero field, but at higher field, it's getting more visible here.
Well, why is it more visible? Isn't it just that it's obscured by the superconductivity? I don't see that it's more visible.
Well, we can compare with the one Tesla to 5 Tesla.
But you haven't. This is a 0 Tesla.
Yeah, this is 0 Tesla. 5 Tesla. Okay. And so in one sample, so we have a very fine field sweep, so you can see how these patterns evolve. So at higher field, we see the checkable patterns are very clearly visible for the fabric flow interference. So in the literature, the fabric flow interference was discovered in other material systems, mostly in carbon nanotubes. So this is about the first report on the carbon nanotubes. They can fabricate electrodes very transparent, with a very transparent electrode to the carbon nanotubes, and then they observe the checkable patterns. So in our device, basically, it covers in the two regions, depends on the strength of the target. So we have the two regions. One is strongly coupled region. So we have a cool pair tunneling because it is affordable to pay the very high charging energy for the cool pair. And then we also have fabric flow interference when the superconductivity is suppressed. And in the weakly coupled region, since the charging energy is too high for cool pair, so it manifests as a single electron tunneling, and we see room blockade. So maybe I should show more data.
No.
Yeah. So
yeah. I mean, the thing is,
weighted at the beginning.
Yeah. I couldn't figure out from the first 5 minutes what you were really going to talk about.
Okay.
So I think the important thing is to start with them when you're going through your talk and so forth. Start backwards, and think about what are the things that are what are the essential pieces of information that you need to provide to get to the main things. Because the data, you flashed it up. It's not that you need more data. What you need to do is to spend more time on that data and setting it up. So, for example, you could give a background talking about you didn't say anything about the implications of Fabry-Perot interference. You're like, okay, we saw it, and that was it. We're recording all this also. So
okay.
But the point is that you want to say, well, what are the implications of having Fabry-Perot interference? It means that you have coherent transport over tens of microns, and you
problem with that is
nothing about that.
Yeah, I think because we cannot really calculate the length of that.
But you know that the length of your device, so it's going to be.
I mean, you can assume that.
Yeah. Okay. So you say that, look, I mean, this is these are devices that are of order of microns, and the length scale is much larger than the 2D mean free path, and so these are things that you need to set up. So, I mean, you also have to remember who your audience is. Which
this is in the transport and nanowire section.
Okay, all right. So, given that that's the case,
I would like
the introduction that you did is more appropriate. Yeah. And that's why I was trying to look it up and to see who is your audience. And in fact, so the fact that you're in that transport thing, maybe you don't need to spend so much time talking about Fabry-Perot in nano tubes.
Okay, I can't delete that slide.
No, don't delete it. I was about to say you need to provide more background, but maybe given the session that you're in, it's not necessary. So actually, now that I know who your audience is, maybe you knew, I don't think you need to change it as much. But I think what you want to do is to maybe emphasize how these measurements reveal a much longer coherence length and higher properties than anybody ever expected. So you could go faster, maybe talking about the superconductivity and other things, and just say these are things that we've discovered, people, oxide community has discovered, and but then spend more time on the things, they say, okay, the mobility is only 10,000 or 5,000 and mean free path. You want to give some basic parameters that they can relate to and say that there is sort of this mystery. Okay, so maybe those systems naively would not be so interesting for quantum transport, but look what we're seeing and look at the implications. So it was me who needed to know who your audience was. And now I actually don't think you need to modify it as much as I was initially thinking. Okay, so let's move on. Who's next? So the one thing I'm going to say is you have to yell. I want to hear you screaming across the room, okay? So you can actually, go hit escape. See where it says rehearse time? No, okay, sorry. One more. Hit escape again one more time. Just say no. See where it says use timings? There's a little checkbox. Uncheck that. Okay. And now, okay, there we go.
So the topic of this talk is ultrafast proposal result of oxide nanostructure. So the electrons will be confined in the interface of LEO-STO central cell, which provides very interesting phenomenon. And the crystal thickness is about 4 unit cells for the superconductor. And also the conductance can be tuned by the circuit voltage. So if we use the conductance AFM, the lithography from one electrode to the other, we will create a nanowire between these two electrodes. And regarding the jump of the superconductance, then we use the negative high voltage on the chip and create the catalyst between the created nanowire. Then the superconductance will drop to the background.
Wait, sorry, just one thing. You keep saying superconductance, so it's conductance. All right, a minor thing.
So the final junction shows the photocurrent phenomenon. This is the experimental setup. So if we focus the laser on the nano junction, it will show supercurrent localized in the nano junction. And we are interested in the physical mechanism behind this phenomenon. So we conduct a series of time-resolved optical experiments. And the reason for doing this time-resolved optical experiment is because this kind of experiments reveal the fundamental timescale for the dynamics involved at the interface, and also provide an alternative way to study the STO samples, and can also see the potential application for the nanostructures at the interface of LEO and STO, such as the thermal spectrum. And this is the photon structure we write at the oxide photodetector. So we first write 4 electrodes on the sample. One is the cell which will apply to strain voltage, and this is the strain electrode. And this electrode is used to measure the voltage difference between the source and the drain. We create a nanowire between the source and drain electrode, and also write another 2 wires. And then we keep a 10 nanometer pattern in the middle of the nanowire. And after prepare the structure, we measure the photoconductance as a function of time delay. And this is our experimental setup. for wavelength at mathematics is about about 51 cents per second. This is the time average for terminal photoconductance as a function of the location. So the signal is localized at where the nanojunction is located. And this is the time result for terminal photoconductance. There are several possible physics mechanisms that may be behind this localized nonlinear although it contains the resonant optical absorption and carrier reluctance region first. But we can really put possible without because the reported lifetime for photoexcited carrier in the XPO is about 7 hours. So in our experiment, the time resolution is about 7 hours. So really we think about the nonlinear K3 process, so they have much greater inherent bandwidth. So due to the inversion symmetry broken at the interface of L1 and Q, the K2 process can do. This process will spread out the entire interface. Our experiment shows the localized junction and also the signal can be tuned by the external electric field. So K2 process will now play the dominant role in this phenomenon. And about the K3 process, since the electric field is confined and also has a magnitude about 10 to the 6 orders. So this process will play the leading role in the nonlinear phenomenon.
Well, that's fine. I mean, there should be a nice pictorial representation of this. Yeah.
So the PC cell is confined, is highly confined in the space, while the optical field is confined in the confining time. So the polarization will, as a result, will be confined both in time and in space. And to prove this, K3 process is indeed the mechanism behind this phenomenon, we conducted a series of nonlinear optical response measurements. This is the amplitude as a function of the source voltage. So from this equation, we know the relation should be linear, and this result gives a perfect match about the.
Not perfect, but more or less linear.
And this is the amplitude as a function of the intensity of the optical light. It's from two devices and also has a linear relationship. This is the amplitude versus temperature. It shows the smallest K3 process at temperature about 30 Kelvin. And this flow shows the polarization, shows the amplitude for different polarization. So if the pump and probe polarization is both parallel, then we have
strong signal. So one thing I would say about this whole thing, this is obviously formatted for paper, but it's too much for a viewer. It's like too many graphs. So what I would recommend doing is breaking this out into separate slides where you're just focusing on one thing at a time. Yeah, I would do that.
For the possible applications in the future, the tailored spectrum can be used to study the property of the XPO, such as the structure phase transition, and also can prove the electronic mass structure in LOSQ nanostructures, and maybe use the single molecule imaging.
So what I would do is, can you go, in this slide, I would advertise NSOC, which is in the same session. So you can say that the double junction results will be described in the talk that is listed below.
As a summary, the photoconductivity of LLSU interface is discovered, and also terms of the optical measurement shows a strong localized response coming from the location of the final junction. And cascade effect is proposed as the dominant physical mechanism behind its ultra-fast response, and also the Hermes response is characteristic.
Right. Oh, sorry. Just go back. So the first point that you have here, I would rephrase it slightly and maybe say nanoscale photoconductivity at the LAO interface. I would certainly put nanoscale, and then, because we're not the first people to discover photoconductivity at the LAO interface, so you want to somehow narrow it down, and then maybe you don't need to use the word discovered, but something else. So just slightly rephrasing at that point. Say yes, yeah. There you go. See, now notice how it tells you how much time you spent on each slide. So it's useful. That's good. So you probably want to save it. Yes, yeah.
Next slide.
That wasn't so bad, right? It was good.
Yeah. Uncheck this.
Yeah, I mean, for first talk, it was great.
Better than mine first time. Thank you.
You just got to work on your volume. That's something you really have to. It was not loud enough.
Yeah, the microphone closer.
No, but even like if you're at a March meeting, how are you going to talk to anybody? It's so loud. I mean, your voice, nobody will be able to hear you.
How big are the rooms at the March meeting?
They vary in size. So some of them can be as small as this room, but some of them are 500 seats.
Here's microphone.
Good afternoon. My name is Alexander Dose, and I'm an undergraduate researcher with Professor Jeremy Levy at the University of Pittsburgh. And today I'm going to present to you work I've done on a project on real-time characterization of nanostructures at the LAO-SCO interface. So nanostructures can be created at the LAO-SCO interface using inductive AFM. And once these nanostructures have been created, the samples need to be characterized by measuring the conductivity between electrodes. But fully characterizing a sample can be time-consuming, so I'm going to present here a technique to fully characterize samples in real time. I might want to get rid of this slide because
No. You want to.
Or you could use the other animation, the one that Guanglei showed.
okay.
But you can decide what you want.
I think you want to remind people.
Yeah, it's okay because this is an important part of the process.
So nanostructures can be created by using an AFM tip with a positive bias applied, and as the tip scans across the sample, a conducting nanowire is created, and this nanowire can be erased either selectively or completely by scanning the tip with a negative bias applied. And by scanning the tip in different patterns, different structures are created. So currently, 2-terminal and 4-terminal measurements are used to determine the conductivity of nanostructures, where a voltage is forced at one electrode and a current is measured at another electrode. But the disadvantage of this method is that you cannot both source the voltage and measure a current at the same electrode. So if you want to fully characterize a sample by measuring the conductivity between all possible electrodes, you have to take measurements in multiple configurations. So, for example, if you want to measure conductivity between electrodes 8 and 3, 1 and 3, and 8 and 1, you'll need to take at least 2 measurement configurations. So the solution we propose is to use a current to voltage amplifier to allow electrodes to serve to both source voltage and measure current. So the current voltage amplifier has a voltage input and an output to sample, and AC voltage is applied that runs through a resistor in the amplifier, and then there's output, which outputs a voltage proportional to the voltage drop across the resistor.
I think you may want to put a more standard type of triangle to represent the differential amplifier here.
Okay, like a triangle here?
Yeah.
Okay, I wasn't sure about that. Good. And this voltage drop is proportional to the current through the amplifier. And one important aspect of the amplifiers we'll use is that the signal from the locally applied bias will filter out. Is that correct?
Well, sure. I mean, yeah.
So we can connect one of these amplifiers to each terminal on a device and apply an AC signal at a unique frequency to each electrode. And then the current measured will have distinct frequency components at each electrode. So the signal we measure at one electrode will be a superposition of multiple frequencies, and we can split up these frequencies into different signals to identify the current that's flowing between any two electrodes. So the advantage of this is it will allow us to do faster characterization of samples, because we will be able to determine the current flowing between every single possible pair of electrodes across the sample all at once. And along with knowing the amplitudes, the applied voltages at each electrode, this will allow us to determine the resistance between any two electrodes instantaneously. And the advantage of this is it will allow us to study either more samples or more complex samples in the same amount of time. So samples on which we create nanostructures with more terminals, it will be a lot easier to study them than it is presently. Also, the real-time results we receive will provide feedback as nanostructures are being created. So as the conductive AFM technique is being applied, we can visualize the state of the sample instantaneously, and thus potentially observe some new interesting effects we didn't expect. So the software we are using to implement this technique is an FPGA, a real-time data acquisition system, and the real-time component allows us to...
It's not just software, though.
The data acquisition system.
Yeah, I mean, you're just calling it software, but yeah.
The data acquisition system we are using is an FPGA real-time system. The real-time component allows for data collection at up to 50 kilosamples per second without any time halt. And so when we receive this data, we can multiply it by a synchronous reference signal to isolate all electrode-to-electrode currents, and thus obtain the conductivities across the sample in real time. Currently, this is only for specific frequencies that are multiple to the base frequency, but we're working on expanding this to be useful with any frequency. And we have already used this software successfully with simulated data, and after having some difficulties with the supplier, we are currently working on acquiring current to voltage amplifiers. So in the figure here, I have some simulated data collected at a single channel, and then using the software and multiplying by a synchronous reference signal, we are able to isolate the conductivity to this channel, channel 1, from all of the other channels across the device. And if we do this 8 times or 16 times or however many electrodes there are on the sample, we're able to fully characterize the device. And we can characterize the device at a rate of up to 500 times a second, or less if need be. And so we can display the conductivities between the channels on graphics such as this one here, where the colors between the electrodes indicate the conductivity of the structure between these two electrodes. So several applications of this technique exist by facilitating the investigation of multi-terminal devices. It will be easier to study larger devices such as transistors and Hall bars, which have more than 2 terminals. And also the real-time feedback during device creation will be very useful to really help us optimize the shape in which we create nanostructures. And it could potentially give us some new ideas into which directions to move for new avenues of investigation.
Yeah, I would say yes, because then it gives you the numbers.
Okay.
Yeah.
I'll probably try to make it longer.
No, I think yeah. I mean, you can add more. I think you can add more detail.
I wasn't sure how long it was going to be. Better too short than too long, I guess.
Yeah.
How often are people over time? Like this actually happens?
Well, I mean, their session chairs can basically cut people off.
Does it happen?
Yeah. It depends on the session chair. Sometimes if they're a wimp, then it becomes problematic because people like to go and they go from one session to another, and if the timings are not right, it can be problematic.
Good morning, everyone. My name is Meng Huang in Professor Jeremy Levy's group in University of Pittsburgh. Today my talk is about PFM imaging of nanostructures created by conductive laser lithography and oxide hydro interface. The material system we talk about in this topic is the luminance thermic interface. It has many fascinating properties. Here I just point out some key properties of this interface. How the two-dimensional electron gas can form at this interface, and it has a critical thickness of the LAO layer, which means when the LAO layer thickness is more than 4 unit cells, the interface is conducting. When it's less than 4 unit cells, the interface is insulating. And also, for 3 unit cell LAO samples, the microinsulator transition happen as the interface can be tuned by a gate voltage. So for 3 unit cell samples, we can use a conductive AFM to write in nanoscale conductive patterns at the interface. Just think about the chip is a bootable local gate. So when we positively pass the chip and move it between the 2 electrodes, a conductive channel can form at the interface. And we can measure the conductance between the 2 electrodes. And when we negatively pass this chip, we can erase the sample, which means we restore the conducting state to the insulating state. And also by splitting the conductance drop, we can measure the width of the nanowire is around 2 nanometers, as indicated in this example. Also, by using the CFM lithography technique, we can make customized nanoelectronics like field effect transistor, which is the transport properties between the source and drain can be modulated by the gate voltages. And also we can make photo detectors. There is a nanoscale, usually around 10 nanometer gap between the source and drain, and if we apply apply light to these junctions, we can measure photo current between source and drain. Also, we can make single electron transistor as the interface, as shown here. An isolated conducting island is created in the interface, which we think it as a quantum dot, and by applying the gate voltage, we can see single electron transistor between the source and drain. So one question is, can we visualize these nano devices? Because if we can visualize these nano devices, we can directly characterize the dimensions of them. But there is a difficulty, which is there are no measurable topographic features for the conductive nanostructures. So we must find some properties of the nano devices, which can give us signals to measure, to visualize them. So the electron force microscopy was also reported to imaging the conductive structures, which is done in Pareto-Bond group. So basically, as we can see here, they can write and cut and rewrite the nanowires and the wires, and they can image them. Basically, the signal comes from the surface charge, but it has insufficient resolution. We can say for a single writing, the width of the wire can be more than 100 nanometers. So for better image resolution, we must improve this method or find some other method which can give us better resolution. And the dense aluminum titanium interface have piezoelectric response, which was also reported in Chen-Bang group. It shows switchable piezo response, and it was done in various LL thickness samples. And the piezo response is associated with the interface metal-insulator transition. You can see here the positive bias table weighted transition and the negative bias table weighted area have different piezo response, which we can utilize to do the to image the nano devices as the interface. So here is our TFM setup. It was done on granular cell samples, so we can bias the chip during the lithography to create the nanostructures as interface, and after that we can electrically isolate the chip during the PFA imaging, and we apply excitation voltages to these two nearest electrodes. We can vary these two excitation signals. After on this talk, we are keep the VAC1 equal to VAC2, and the piezo response is measured by the vertical deflection of the probe. So what we did is first we can write a structure and showing this figure. Use 10 volts capacitive to writing a rectangular area, and then negative 10 volts erase a square in the center. And then we tuning the reference frequency at the lethal area and the non-lethal area, which we can find the reference frequency. And we can see here the lethal and the non-lethal area, the amplitude of the piezo response has a difference. And we can use this difference to make a TFM image as shown here. So we can clearly see the structures we write before. And also if we measure the piezo response as a function of backgate voltage at different at the lethal and non-lethal area, we can still see the variance between the piezo response. Okay, so we can use this method.
But you don't actually explain why one is hysteretic and the other one is not hysteretic.
Yeah, I can explain it if someone.
Well, no, but if you're highlighting some difference,
okay,
it's kind of cries for an explanation. But anyway, you keep going. I mean, you could also just skip that thing, because I think it's not clear that that's
okay.
necessary, because, you just want to show the line.
So, the first create is the single wire. and we can monitor the conduction change during the writing. So from the conduction drop, we can rate the wire width is around 11 nanometer, and then we can use the PFM method to image the wire, as we can see here. And if we extract the horizontal profile of the wire and weighting it, we can get the flow width at half maximum is around 30 nanometer, which means at this point the wire width is measured in PFM imaging method is 30 nanometer. And if we extract the horizontal profiles as a function of the y-axis, we can plot the flow width at half maximum as a function of the y-axis. So from this statistical data, we can get the average of the nanowires we created. Also, we can image in parallel wires, showing here from the left and the right. The writing parameters is changed from 200 nanometer to 1000 nanometer, writing with 8 volts bias voltage, and then cut in the center by a negative 8 volts bias tube. And we image all these 5 wires and measure the wire weight of them. So we can say the wire weight is varies as we change the writing parameter.
Which one is to the voltage? Is it? I mean, when you're applying any voltage to the tip, to the wires.
Yeah, I apply EC1 and EC2.
Yeah, but to which side? The top side or the bottom side?
Both sides.
Oh, you're applying to both. Okay. Also, if we take the vertical profiles of these three wires, we can measure the gap size of created at the center. It also changes as a function of the writing speed. And here, the width WC, it means the wire width measured from fitting the conductive drop curve. And WPFM means the wire weight measured directly from the PFM image of the wire. And by plot these two, we can get a linear fitting result as this, which means there is a 25.6 nanometer convolution between the chip and the sample surface, which makes the wire weight measured from PFM larger than the wire weight measured from the conductance staging. And from this staging result, we can deconvolution the PFM mean. Yeah, I think you can do this in a more illustrative way. So, for example, you could show a writing and a cutting, and then you extract that, and you get a certain number, and then on the other side you show an image where you get the width, and then you take those and you put 1 point on your graph. And then you say, we repeated this 25 times and under different conditions, and this is the relationship.
Okay. Yeah.
Because WPFM, WFIT, people are going to tune out. They don't know what that means. Don't expect them to remember what your symbols mean. Okay. So you want to help them as much as you can.
Here you can also show. One is your nanowire image, the other one is showing the cutting to figure out the wire width. People maybe gonna forgot how you fitting the conductor job curve. Maybe people don't know.
Okay. Just change the sensitive to picture.
Maybe you can just put the two images how you extract the wire.
Just said that.
So from this relation we can convolution the PFM results to get the actual dimension of the nano devices. So here I want to talk a little bit about origin of the PFM signal. So
proposed origin.
Oh, the possible origin of the PFM signal. Yes. So we think the electrons accumulated at the at TO layers near the interface can lead to structural transition with the antenna distortion. And this measure has the deviation to calculate and also experimentally measure. So we think the hydro distortion happen at the STO near the interface can produce a PFM response. Okay. As a summary, we do PFM response, we measure PFM responses per unit of area STO interfaces and utilize them to image nanostructure. And we image single nanowires can be as small as 30 nanometer, and also the influence of the writing parameters can also be visualized in the imaging. And we think the possible prolonging of the signal due to the young distortions of the pattern.
Yes. So did you cite the first paper that shows? I guess you did maybe on slide 6. Can I see slide 6 again? Yes. Okay. Good. Yeah. So that's good. Okay.
Okay. Here and also I can put a phone. I can advertise phone and talk about this.
Mm-hmm. Yep. Okay. That's good.
Your name is Schwab?
Well,
No, you should put your name.
Matt,
Doesn't matter. You should say I'm giving the talk for Shirley.
Alright, so, good morning, or good afternoon. So I'll be talking about, parallel, AFM writing of the APS Clamp-Film Illuminate Joining Titanate interface, using, one-dimensional, multiple tip array. Alright. So, I want to motivate this talk by, looking at Moore's Law, which, many of you have probably seen this graph many times, but this is, intended to show, I don't know what this is showing, but I want to show that Moore's Law has been valid for many decades. And,
Yeah, this is not the traditional Moore's Law. This is more like the beyond Moore's Law. So it's like you want more than more and more. So more is the...
I might put something else. My intent is to look beyond Moore's Law, and so that's how I'm setting up the talk. You've already heard in this session several talks about LEO-SPO-based nanoelectronics devices, and there are several results that that may make this system applicable to room temperature electronics that go beyond Moore's Law. For example, we can make diode structures and 3-terminal transistors. We've been able to show that these transistors are able to operate at gigahertz frequencies. And also we have more recent published results showing that although oxides generally have very small mobility, when we form nanowire structures in these oxides, we actually have enhanced mobility. So there'll be a little graph here showing that. So maybe the system is promising for those reasons I cited, but there are several challenges. One is scaling the substrate on which we write on. So right now, we have a lanthanum illuminate grown on top of a strontium titanate substrate, which are limited to about 5 millimeters on the side. And what we want to do is look at growing the LEO-SPO on a scalable substrate. So this has actually been demonstrated on LSAT wafers and silicon wafers, which can be grown up to 8 inches and 12 inches respectively. So this has been shown and Zhengbao screw. So a second challenge is increasing the writing process itself. So right now we are using a single atomic force microscope tip, and we're able to create one transistor. What we would like to do is scale the number of tips so we can write in parallel multiple devices at a time. So just again, a reminder of what we're doing here. We're taking a conductive AFM tip, applying a positive bias. When we scan that across the surface, we create a conducting nanowire at the interface. And if we apply a negative bias to the tip, we can then either erase the entire structure or put a potential barrier in the wire. And by measuring that wire, we can, by measuring a conductance drop or by doing PFM imaging, as you just heard, we can extract the width of these wires. So this will be about a background about multiple lithography. So this has been shown by IBM and Chad Murphy's group at Northwestern. They can use these multi-tip probe arrays to do different kinds of patterning. So they can do some optical patterning, maybe some imprint patterning. So we'll set that up.
Right. Yeah, so you want to make a distinction between the cantilever-based approach of the millipede and the cantilever-free approach, which has millions of tips.
Okay. Okay, so these, I guess I should say the Chad Merkin's group has been able to demonstrate individual control at the tips by using a phase array mask or something like that to control light that is hitting each probe. But the challenge for us is we need to have individual electrical control at each tip. So one possible solution to doing this is, instead of applying the bias to the AFM tip itself, applying it to the electrodes on the surface. So here we demonstrate that if we ground the AFM tip and apply a negative voltage to the electrode, we are indeed able to write as if the electrodes were grounded and the AFM tip was positive bias. Okay, so the next thing we demonstrate is parallel writing. So here we replace the single AFM tip with a one-dimensional probe array, where all of the tips are electrically connected to each other, and we apply we monitor the conductance between two electrodes on the surface that are far away, electrodes in between them, floating electrodes in between them. So this experiment has a positive bias on the tip, and if we move the probe array in the direction indicated by the arrow, we write wires in parallel between all the electrodes. And you can see the result here is a jump in conductance between electrodes A and B. This is an image of the probe array in the electrodes, which is kind of big. Okay, and finally we combine the parallel writing with individual electrostatic control. So in this experiment, we first bias this probe array to write a wire, an isolated wire here, and then we apply different voltages to the electrodes on the surface.
With the probe array grounded.
Okay, yeah, with the probe array grounded. So we first write wires between wires beginning at electrodes 1 and 2, going to that, I don't know what we call it, a bus wire or something. And then in a later step, we write only a wire from electrode 3, and we can see that we're going to successfully do that. Okay, so
what I would say is that in this graph, I would maybe do a reveal, a slower reveal, so people can focus on things. And I think we have more data than this, right?
Probably.
Yeah, so you probably want to add that also.
Yeah.
I just tell the full story.
Okay, so we demonstrated we can do parallel writing with visual control of each step in a 1D array. This is great promise for increasing the throughput of this conductive AFM lithography. Next steps are to start investigating writing with two-dimensional step arrays. Something else. Thank you.
Okay. So who's next?
Yeah.
Okay, good afternoon. I'm Yan Junma from Germany School. Today I will be telling you how to generate and detect the terahertz field by using nanoscale oxide structures. Before I get to that point, a little bit background information can be helpful. First of all, what is terahertz? Terahertz frequency is defined as a frequency bandwidth, roughly from 100 gigahertz to somewhere around 30 terahertz. This frequency bandwidth is a characteristic frequency for different intermolecule and intermolecule collective vibration. Because of this feature, people have been using this frequency to study the configuration of different molecules. One thing I should mention is that so far people have been looking at a large number of molecules. The interaction between terahertz field and a single molecule has not been explored yet. The research for molecules is not the only thing that terahertz can be applied to. Different fundamental problems can also be addressed with the help of terahertz field. As an important example, the terahertz time domain spectroscopy can provide useful information in chemical sensing or substance identification and so on. Because this frequency is so useful, a lot of research about terahertz generation and detection is going on. One problem, like I mentioned in the beginning, is that the terahertz spectroscopy for a single molecule. The difficulty is that we do not have a terahertz detection scheme that can provide high enough resolution to look at a single molecule. To overcome this difficulty, as we propose here, is to use the nanostructure at the interface of lithium aluminate expansion kinase heterostructure. For those of you who have been sitting in this room since the beginning of this session, you must have seen this animation for a couple of times. So again, this positive voltage can be used to create nanostructure, while your negative voltage can be used to erase them. With this technique, we can create a nanoscale photodetector at the interface of this oxide heterostructure. This figure shows the typical configuration for the nanoscale photodetector. The insulating gap in the middle is about 10 nanometer by 10 nanometer area. Once we have this detector ready, we can focus our laser onto the interface and scan the light over the sample. By doing that measurement, we find signal comes from where the junction is. Although in this measurement, the spatial resolution is limited by the diffraction. So you may wonder how we can claim the photoconductivity comes from the nanojunction. One argument is that from the simulation, we see the electric field from source wires is strongly confined around the nanojunction. And a second evidence is the stark shift we observe in the measurement. By combining these two, I think it's convincing to say that this nanojunction is photoconductive. In order to understand the dynamics behind this photoconductivity,
as Lucy discussed earlier in this session, we did time-resolved time probe measurement. By focusing the ultrafast laser pulse onto the junction and measure the voltage across the junction as a function of the time delay, we find that the response is ultra-fast in time, and also it's well localized in space. It can only be seen around where the junction is. This special temporal confinement is due to the high-speed process in expansion kinase. The DC field, which is strongly confined around the junction, provides spatial resolution, while the ultra-fast laser pulse provides the temporal resolution. And by combining these two, the resulting nonlinear polarization is well defined in both space and time. From the literature, we know this high-speed process can give rise to terahertz generation. And now, since this oxide nanojunction also shows this third-order nonlinearity, so let's see if we can get terahertz out from this oxide nanojunction as well. To explore that possibility, we make two devices under the interface, separated by microns from each other. And for device A, the pump is focused on device A, and the probe is focused on device B. And the voltage across junction A is measured at frequency, well, the light focused on device A is modulated at a frequency FA, and the light focused on device B is modulated at a frequency FB. Then the voltage across junction A is measured at a frequency FB, and the voltage across junction B is measured at a frequency FA. In this configuration, we use one junction as the source and the other one as the detector. And the data here shows the overlap between scanning photoconductive image and the reflection image to confirm the position of these two devices. And the separation between them is about 12 microns. And this is the data we measure in the time domain. And several features I want to point out based on this measurement. Let's take the red curve, for example. Number one, we see the signal, and we do not see any interference in the signal. So that means this response cannot come from the interaction between optical fields.
And nobody's going to get that. That's a very subtle point, which is not illustrated by your slide at all, and nobody will know what you're saying. So if you really want to make that point, you're going to have to put in a slide or something to show that you see interference in one case, one experiment, and not in the other. The other thing is that this slide is also very busy. You have lots and lots you're packing so much stuff into one slide. You might want to consider breaking it out, or at least revealing slowly certain things so that people know what to look at.
Okay.
You could even put little boxes, and then you can, have the border which moves or something, so that people know. You could show just the diagram, make it full screen, then shrink it down, and then reveal those two images and show where they come from, and then move over and then show this and then show, something. But you got to guide it's too much stuff.
And number two is by measuring these two devices at the same time, we see the response from two devices are separated in time. This separation is due to the propagation of field from one place to the other. And number three is by doing the Fourier transform for the time domain result, we see the bandwidth goes to terahertz range. So based on this measurement, we think the signal is from the interaction between the optical field and the terahertz field. The way we understand the propagation of terahertz field from one place to the other is shown in this illustration. Due to the complexity of our sample, the terahertz field can take more than one channel to travel from the source to the detector. And because both oxide materials show very strong dispersion in terahertz bandwidth, so the component traveling in vacuum is the fastest. And because of the range we scan in the time domain, we think we only capture the component in the vacuum. I can also explain why we do not see any signature in time domain about the interaction between terahertz field and the material. So as a summary, we identify this third-order nonlinearity in the oxide nanojunction structure, and we also demonstrate that by using this nonlinearity, we can generate and detect the terahertz field.
I would put fewer words here, put some pictures on the right-hand side, like your illustration of how you get the spatial-temporal resolution, and then show the two graphs, two curves, some iconic data that summarizes what you've done.
Okay. Yeah. So my talk ends here, and thank you for your attention.
Okay. Enable editing.
Quantum simulation session. An idea.
That's good.
Okay, so I'm Megan Kirkendall. I'm in the Jeremy Levy group at the University of Pittsburgh, and I'm going to be talking about experimental one-dimensional quantum simulation using an oxide nanoelectronics. Okay, so the first thing I want to do is introduce our system a little bit. We have a lanthanum aluminum oxide and strontium titanium oxide sample. So we have strontium titanate and lanthanum aluminate, and at the interface between these two insulating oxides, there's a quasi two-dimensional electron gas that forms. And there's also a critical thickness. So for 4 unit cells of lanthanum aluminate, we see that the interface is conductive, and for less than 4 unit cells, the interface is insulating. And when there's exactly 3 unit cells of lanthanum aluminate, we see that this interface is tunable with the backgate. So when a positive backgate bias is applied, the interface becomes conductive, and when the bias is turned off, it stays conductive. And then when a negative backgate voltage is applied, we see the interface go away. So there are also some other interesting properties of this interface. We see the high mobility two-dimensional electron gas and the metal insulator transition that I just talked about. There's also superconductivity at the interface, magnetism, a strong spin orbit coupling, and we have the ability to write nanostructures and nanodevices at the interface. And the way we do that is with conductive ASM lithography. So we have 2 gold electrodes here that are contacting the interface between LAO and SPO. And if we apply a positive voltage to an ASM tip and scan across the surface, we're able to create a nanowire at the interface here. And so we see an increase in the current when this wire is completed. We're also able to cut the wire by applying a negative bias voltage to the tip. And so we scan across the wire, we see a decrease in the current, and there's able to characterize the width of the wire. We're able to achieve wires of about 2 nanometers. And so one of the things that we can do with this technique is create a sketch single electron transistor. And so we see that we're able to, we have about a 1.5 nanometer conducting island at the interface. We can control the number of electrons with side gates. So you can see here, this region here is where there are no electrons in the connecting island, and we can control, by increasing the side gates, we can control the number of electrons in this island. So this is like a solid state atom. Okay, so now
your voice tends to trail off. You're gonna keep projecting.
Okay. So now I'm gonna switch gears a little bit and talk about quantum simulation. So what we want to do with quantum simulation is design and control quantum systems which can simulate important Hamiltonians that we're interested in. And currently a lot of work is being done in this with cold atoms. And cold atoms are a good system for quantum simulation because they're very controllable. You can control the lattice geometry, and so you basically control everything about your system experimentally.
And the system is very well understood.
And
also.
Very well understood.
Yeah.
And so, I forget what I was going to say about simulation. But you can also control and study the unitary dynamics of the system because they have a long coherence time, and unitary evolution so they have a coherence time of about on the order of seconds, and unitary evolution on the order of milliseconds. You can easily study unitary dynamics, and they're an excellent system for engineering quantum states. And so what we're interested in is doing the same type of thing, but in a solid state system. So using the nanoscale control that we have over the LAO-STO interface, we hope to use this as a quantum simulation platform. So, okay, so so the system naturally supports superconductivity, which will allow us to alter the Hamiltonian of the system with our nanoscale control, and maybe create a new class of what we're calling meta superconductors to try and study superconductivity in the system. Okay, so our goal is to, our first step is to try and simulate experimentally simulate a one-dimensional system. And so our first step is to characterize a nanowire. Eventually we'll want to create like a one-dimensional array of dots or a wire with barriers, but because that's difficult, the first thing that we've tried is a nanowire with a sawtooth modulation. So the structure looks like this. There's a 60 nanometer sawtooth in our structure, and then a straight portion of the nanowire. And so what we see, so we're able to see superconductivity in this nanowire. So this is varying the magnetic field. We see superconductivity in this nanowire, and then this is the zigzag portion of the wire. So we see there's definitely a difference between the two portions, and there's a lot of inherent noise in this zigzag channel that we can try to understand.
So your voice is really trailing off.
Okay, sorry. Yeah. Sorry. There's supposed to be a summary.
Okay. Yeah, it's interesting. I was looking at the other talks in the session. So the people who call themselves doing experimental things, what they really mean is they're doing numerical simulation. So I think there's only one other real experimental talk in this, which is, I think after it's the very last talk, opening up the quantum three-body problem with undetectable measurements. But I think most of the people in your, what you should really do is read all the abstracts, and just so you know who are the other people in the audience. But I think overall it's good. I think what you may want to do is spend more time contrasting our platform with the cold atom simulator, which you're still working on the talk. But sort of like have a table, like what are the strengths, what are the weaknesses, or what we think. So the strengths are we can go to much lower temperatures. We can see superconductivity. It's highly reconfigurable. And we may be able to scale it up and have more arbitrary shapes. The downside is we don't know what's going on in the system, right? It's not well characterized. We don't know a lot of the physics, but we're interested in the physics. So, it's sort of, we're at the very beginning phase of this. Okay, so who's next? Michelle. You're in the same, which session?
Oh, wait, which one? The
G section. Yeah, but it's a different one.
Somehow didn't get put in.
I have C27.
I thought I put all this stuff in. It says G12?
Yeah. Oh, G. Oh, sorry.
G12. G12.
sorry, what was the session?
We were just trying to figure out what session you were in and so forth.
I don't know.
Yeah, no, it's now we know. It's G12. But I don't know which.
What?
12 point something, yeah.
Oh, okay. My name is Michelle Tomchek, and I'm a graduate student at the University of Pittsburgh. And today we'll be presenting some recent data on the effects of gating on lithium aluminate strontium titanate heterostructure devices at low temperatures. So while lithium aluminate and strontium titanate are both insulators in bulk, there's a polar discontinuity in the layers at the interface, causing a potential difference that diverges with the thickness of the LAO grown on top of the bulk strontium titanate. And after a certain critical thickness of lithium aluminate, a polar catastrophe happens where half an electron of charge shifts from the top surface, or shifts down to the interface with the STO, forming a quasi-two-dimensional electron gap. So it's important to know that there are multiple carriers in the system due to the Z confinement at the interface. The DXY band gets pulled to a lower energy than the YZ and XZ bands, and this is seen in transport measurements. There's a critical carrier density at which the DXY, or at which the DYZ and DXZ bands become occupied, and this transition
yeah, so the transition is associated with a lot of things like, yeah.
And so then as we go across this transition, we see a spike, for example, in the spin-orbit coupling greatly increases, causing the crossings of these bands to open, mixing the X, Y, and then the XB and YZ bands. And then also in the system below the critical temperature of about 200 millikelvin, superconductivity also opens a zero bias gap. And so there's a lot of inherent phenomena occurring at this interface, like the strong spin-orbit covering, the low temperature superconductivity, as well as built-in ferromagnetism. And so understanding and controlling, being able to control these different phenomena will allow us to create novel devices. For example, due to these different features, the system is proposed to potentially host Majorana fermion state. And oh yeah.
You can change the
reference to change the change your reference to.
I mean, put some reference.
NIAX reference.
Well, not necessarily. I mean, this is still more of like the background, right? So.
Okay. Yeah.
So controlling this transition at the interface, well, clearly the growth conditions are important, and so if for samples, for heterostructures that are grown with the LA of just below the critical thickness at which the two-dimensional electron gas forms the interface, a positive backgate applied to the sample can induce that transition, consume the device through this metal, through the interface through the metal insulator transition. And so in that same way, we use conductive atomic force microscopy, microscopy to apply a top gate which locally changes that interface, allowing us to write nanostructures on these devices, or on these samples. And while these top gate and back gate writing are voltage output writing processes are very hysteretic, allowing these devices to live long enough for us to characterize and use them in experiments. We can also capacitively couple to the channels using side gates that we write. And so these side gates are, one reason they're very useful is due to this high dielectric constant in the SPO. And so then we've performed experiments where we can tune the superconductivity, spin-orbit interactions, non-local effects. And actually, should I put like a reference to like the non-local? Because are you doing gated non-local?
Yeah.
Yeah, I could put a reference.
Yeah, you could put an advertisement.
Although I guess not till Friday, a few days off. But
well, that's all the more reason to
okay.
put an ad for it.
So here's one device in which we have two long side gates, and then a point side gate on the other side.
Are you going to show power lab view graphs, or are you going to?
No.
Okay, so this is just a placeholder.
Yeah.
And I think also, I don't know, I'm not a big fan of these, the topologically correct but
Yeah.
geometrically possibly misleading diagrams. I think it's a good idea to show the actual types of structures that we're really creating. And also, in this overall slide organization, you don't want to tuck away your data to the corner.
Okay.
So really what you should do is, I would make that really big, like 2/3 of it.
Okay.
And then you can write, these talking points are really for you.
Yeah.
I mean, you just want to make sure that you're saying things and then you're sort of summarizing in as few words as possible the main talking points.
Yeah. Okay. Yeah, I guess I wasn't really formatting the font too much.
That's okay. That's okay. But I mean, but the point, I'm just saying that when you revise the talk, make the graph and the data bigger. If you really want people to see what's going on, you're going to point to all the key features.
Okay.
And the other thing is that all this white and purple stuff, see if you can suppress that, because I don't think you want to really, that can be misleading. You know, the eye will look at this and doesn't know what to look at. You know, we've been studying these for a long time, but I would also try to take the suggestions also that Sergey was saying, like, let's start looking on these on the log scale, try to work out a color scale that's going to reveal all the interesting things.
I think you want to make sure your axis will be clear too, like these 14 means nothing.
Yeah, and people are not going to know what those things are.
Like
I mean,
draw.
like 4-terminal voltage. Or
I would draw a voltmeter measuring 5 and 28 and show where I is.
Yeah, and if you just want to call it V, call it V. Don't put a lot of subscripts that are meaningful to us, but will be overwhelming for the
Igor thing, but I wasn't sure how much.
Yeah, I would just say that when you have your schematic, you can start overlaying voltages and currents and
you
make
shouldn't
it clear.
be shy about just talking through that and setting up the measurements.
Yeah.
Because there's like a million things going on there. And just to show.
Yeah, there's so many
here and voltage.
Yeah, and I think also when you showed those 3 in the previous slide, you're going to scare people.
Yeah.
I wouldn't even necessarily show that until the end, maybe. You can say, oh, look, we can make lots of different devices.
Okay.
Just when you show the first device, walk people through it. It's better that they understand fewer things and more deeply than, trying to go through too many things.
Okay. So in this particular device, we're sourcing current across leads 1 and 4 and measuring the 4-terminal voltage across leads 28 and 5. So our main channel here is being affected by these 3 side gates on leads 2, 3, and 27. So in this intensity plot, the z-axis is the conductance, and we see the superconductivity zero bias peak. And changing the color scale, you can see that as the side gates are decreased, the width of the peak, the critical current narrows, and the peak itself is also changing. It's also being tuned with the side gates, and then it's also sort of interesting to note that past the breakdown voltage at which the gate starts leaking, we see that superconductivity abruptly vanishes. And then, sorry. Over. So in this device, we're again sourcing current. I think it was sourcing current 28.5. I can verify that, and measuring voltage across leads 1 and 3. And in the 4-terminal measurement, again we see a change in state, a change in the superconducting state as we sweep the side gate. And so I was starting to make Igor graphs showing the IV curve.
Yeah, I think actually even on the first slide that you show, there you want to show some IV curves.
Yeah.
Because this is a more abstract way of looking at the data.
Yeah, I have 3 IV curves from 3 different side gate values. And then I was going to highlight them on the 2-dimensional messy plot. Sorry, I keep touching the screen.
Yeah, that Igor plot you have there could be the first set of data you show in the talk, because it's easy to understand.
Okay, to see how the,
Mm-hmm.
we can easily see that the normal state resistance is changing.
Yeah.
Yeah.
And while all 3
You want
lines
the
do have
process.
superconductivity, there's an abrupt change with the superconductivity.
Yeah, and you only have to process 3 curves. Like, the viewer's mind only has to process 3 curves instead of this
Like, an
2D
Mhm.
plot.
Yeah, okay. Okay. Yeah, so this is good. So I can use this. And then, we can also tune the spin-orbit interaction, in these devices. Here, we have 3 different backgate values applied to the device. And so first, at 0 backgate, we see that as we change the side gate, okay, I guess that's prepared to explain. Okay. So we're looking at the longitudinal resistance across the main channel. And so for various side gates, as we increase the side gate, we see that while the magnitude of the normal state resistance decreases, the curvature is increasing.
Well, you need say weak anti-localization stuff.
Okay.
Specific point out.
Okay. So from this, we can see that the larger curvature means we're tuning to a larger spin-orbit coupling as we increase the side gates. And so then we repeated this measurement for various backgate values. And then I have a couple additional slides that I wasn't sure if I was going to talk about the examples or not.
It's complicated. It's
Yeah,
not
because that's,
outside.
yeah. And then, where did that? So I wasn't sure if I was going to include those or not, but, yeah. And then I don't have a summary slide yet, but.
Are you going to show any backgate dependence?
I wasn't going to talk about it as much. I mean, there's a little bit of it. You mean of just as, like, the superconductivity?
Yeah.
I mean, I guess so. I'm pretty sure we have it.
Yeah, we have it. In some very early stage, we have a backgate dependent superconductivity.
I can show you some fun.
I think that would be helpful.
And I don't think that's ever been shown at a March meeting either. So you could do that.
You spend time talking about the band structure, but then
Yeah. Oh, I guess
Didn't tie in.
it doesn't.
I guess in my mind it was motivated because they gotta be changed.
I know, but then somehow it'd be nice if you could relate that and say that, we're tuning through these different bands and trying to understand how that relates to the super. And the other thing is that the superconductivity should peaks at this Lifshitz transition
Okay.
in the bulk. And so we're trying to understand how that happens locally.
Well, the introduction part, maybe you can use other people's slides. And
Oh, you don't have to. I mean,
it's not in the same session.
even if it is, I mean, if you want to make your own slide, you should make your own slide. But you also could, what Guangle is saying that you could
Like, yeah.
use and recycle some of the other slides.
I think you could spend more time just background of the system. I think.
Yeah, I mean,
I don't know what the other talks are in the session, but these people may have already been in session C12 and seen everything already. But
right. So it's actually refreshing to see a different take. slightly different take. So, and that's it. That's the other thing is that you should, everybody's introduction should be thinking about how your introduction ties in with what your message is. So you can emphasize in your introduction the points that are most closely relevant to what you're going to say, so that everything fits in nicely and ties in well. So I think it's okay to take a fresh look at the introduction and to think about what is the most important thing. So, but if you also want to just take some slides, that's fine.
Hi, good morning, everyone. I'm Feng Bi from Genetics Group at University of Pittsburgh. And today my topic is about the capacitance characterization and electromechanical response of top-gated lens-aluminum joining titanium heterostructures. In 2004, Harry Huang first discovered the high-mobility quasi-2D electron liquid at the well-defined interface of lens-aluminum joining titanium. And such interface will undergo insulator to metallic transition as the LL thickness increase. And also the conductance of the interface can be tuned through the metal to insulator transition by basket bias. Further study shows that such kind of metal to insulator transition at interface not only can be tuned by the basket voltage, but also can be tuned by the top gate voltage. And it is confirmed by both the IV measurement here and also the capacitance measurement here. And both of these kind of measurements show the hysteresis behavior. And another interesting phenomenon is the capacitance enhancement near the metal insulator transition region. In 2011, Lu fabricated these two-terminal capacitor devices based on this 5-unit cell and 12-unit cell LO1 Such two-terminal capacitor devices consist of circular metallic top gate and this conducting plate. And they observed the capacitance will substantially exceed the geometric capacitance value right in this electron depletion region at the interface. And such observation was happened both at the room temperature and also at this low temperature. And also this kind of capacitance enhancement phenomenon shows a strong frequency dependence. So as the excitation frequency increase, this kind of capacitance upturn will get suppressed. Also, in Chen-Bang's group, the piezo response microscopy study was also reported in this LLSQ system. This hysteresis behavior was shown during this metal insulator transition at the interface. So we want to understand those kind of transport measurements, this hysteritic behaviors, and also this capacitance enhancement phenomenon. So that we combine both this capacitance measurement technique and also the piezo response measurement in our study. So our samples are 5-unit cell and 12-unit cell LL on SQ grow under two different conditions, which is similar with these previous studies. And we also fabricated this kind of two-terminal capacitor structure with the circular gold top electrode and also the arc-shaped electrode that directly contacts to the interface. Such contacts to the interface are ohmic, which is proved by doing this RV measurement between two of these electrodes connected to the interface. And also it shows that there's no Schottky barrier measured at this gold interface junction. And here is the setup for our combined capacitance and piezo response measurement. So for this device, the top gate is virtually grounded to eliminate this.
Okay, so here, Feng,
yeah.
I would make the whole diagram bigger, use the full width of the thing. You can push down the text and just expand everything so it's the full width.
Okay.
That's one thing.
Yeah.
Second thing is you can reveal and highlight the different, there's so many things going on here that what you should do is just show like show the AFM, then going to lock-in 1. Then show one thing, and you can even suppress the other things. Yeah. And then you can show them all together in the end. So you just show one thing, show how you do the PFM, then suppress it, show how you do the capacitance measurement, and then put them all together.
Yeah. Okay.
But make it bigger.
Yeah. And we'll apply the DC bias to the directed to the in-phase to modulate the melody insulated transition at the in-phase. And also there are two circuits here in the graph. Like the red circuit represents what we use to measure the piezo response signal, and the green circuit is the capacitance bridge that we use to measure the capacitance signal. And here is the piezo response measurement and the capacitance measurement. So the capacitance measurement here shows the in-phase can be modulated on the melody insulated transition by this DC bias. So as the DC bias decreases, the capacitance signal will get strongly suppressed when the electrons at the in-phase was depleted, and it will restore when the top gate bias increases. And for the PFM signal, we see the similar behavior. So basically, the signal gets suppressed when the in-phase becomes inflating, and get intense when the in-phase becomes conducting. And both of these measurements show hysteretic behavior, and the hysteretic behavior are all in the counterclockwise direction. So to understand this, we did this simultaneously piezo response and capacitance measurement.
So again, here, so there's sort of a mode for print figures, and then there's a mode for talk figures. So with this, you want them to look at one at a time. So just show one at a time. Don't show B and C. You don't need to use. You can suppress the A, B, and C. First of all, because they don't refer to anything.
Yeah.
So then you just show that one, and then say what you want to say about it. Then show the second one, then show the third one. So walk them through it.
So basically, in-phase was tuned to the insulated state, right at the transition state, and then to the conducting state. And we find that there is a strong correlation between the capacitance signal and the piezo response signal. And so that means these two signals are strongly connected. And to understand this, we did a detailed study about the piezo response signal. So basically, we tracked this resonance frequency about the piezo response spectrum. And we find that there is a resonance frequency shift as the DC bias change. And such kind of resonance frequency shift also shows the hysteresis. So all this indicates there could be a structural distortion happens in our devices. And the quantitative piezo response measurement was also cognitive piezo response analysis was also applied to the measurement. So this figure shows the piezo response spectrum taken on the different sides. And from this spectrum, we can feed it to from each spectrum to a simple harmonic oscillator model and extract the vertical tensor component as this. And by doing integration, we can calculate the structure distortion, so which is shown in this graph. So such kind of structure distortion could come from the in-phase, could happen at the in-phase. This is reported from previous studies. For example, the STM experiment shows that there is a dilation at the in-phase of the LLM field. Also, this theoretic density function theory calculation shows that at the in-phase there will be a structure elongation happen. And our measurement happened to show a similar value, a distortion value as this previous report. Thus, we propose such structure distortion could come from the in-phase. And here will be the possible mechanism for this distortion happen at the in-phase. So we propose this would be due to this Young-Taylor coupling. So as we tune this DC bias, the electrons will enter or deflated to the in-phase. So this two process will result in this cubic to tetragonal distortion of this TiO2 in this STO near the in-phase. So that will contribute to this distortion at the in-phase. And such a distortion at the in-phase will give rise to a TFM response as well as this hysteresis behavior. And another thing we are trying to figure out is about the capacitance enhancement phenomenon. So we did this capacitance measurement at different frequencies, and this frequency dependence of this capacitance enhancement was reproduced. So to understand this, we did the time resolved piezo response measurement by switching this DC bias between positive 2 volts and 2 volts. We actually measure the piezo response, the response time of the piezo response signal, and we find that this response time for this piezo response signal was around 11 milliseconds and 12 milliseconds, which correspond to a frequency around 91 Hz and 18 Hz. Such a frequency matched well with the frequency dependence of the capacitance signal. And also we performed this two-dimensional spatial resolved TFM image under the top-gate controlled metal insulated transition. So as we change the base bias, we find that this piezo response, this 2D TFM image shows this homogeneity features, and such small TFM islands show signal change, which we believe is showing the charging and discharging process. And the figure F shows the signal difference between these, which actually shows how this charging process happens. And we hope this kind of TFM image to be provided some better understanding of how this capacitance enhancement phenomenon. So here is our possible explanation about this capacitance enhancement. So such capacitance enhancement could be due to this orthogonal distortion happened at this in phase. But the uncolor effect will make a band splitting, which may result in this capacity enhancement phenomenon. And also the frequency dependence of this capacity enhancement is due to this kind of structural distortion will have finite response time. So
So
summarize.
You're saying that the 100 hertz frequency response is due to the structural, or I mean, I thought we were saying in the paper that it was more due to like the energy barriers and the time that it takes for electrons to move from one trap to the other. I think it's because that scale is really fast. I mean, when you measure resonant piezo response at hundreds of kilohertz, that's due to the electrons moving a little bit, but then. And do you think the funding sources, or is that in the first slide? Okay, that's fine.
So my name is Josh Beasy. I'm a postdoc at the University of Pittsburgh, and I'm going to be talking about signatures of non-local transport in superconducting oxide nanostructures. And the materials we're looking at here are at the interface of lanthanum aluminate and strontium titanate. Samples are grown by Cheng-Long Holmes Group at the University of Wisconsin, Madison. So if we think about why superconducting nanoelectronics are interesting, it's because we have pairs in reduced dimensions, down to the level of single Cooper pairs, such as the Cooper pair box used as a qubit. We have a single Cooper pair coupled to a reservoir. A lot of people are interested in Majorana bound states, which are in topological superconductors. So these are useful for quantum information processing. They have very good coherence. In addition to that, you can look at entangled states of electrons from, say, splitting super pairs and superconducting and metallic junctions. And Cooper pair injection similarly in the edge states of a quantum oscillator. So related to that last note, there are a few known non-local transport processes in superconducting nanowires and nanostructures. One is cross-Andreev reflection. So this is distinguished from regular Andreev reflection, where an electron will, in a normal metal, will come to the interface with a superconductor, and in order to be transmitted as a super pair, it will reflect the hole backwards. Cross-Andreev reflection is a non-local process where if two normal leads are separated by a superconductor, and the separation is less than the coherence length of the superconductor, then rather than reflecting the hole backwards into the normal lead, an electron will be paired with another electron in the other normal lead, and the hole will be reflected in the opposite normal lead. So the resistance in this process can be negative or positive. We define resistance as the non-local voltage measured here divided by the local current here. It can be negative or positive. It generally happens at low bias, and it's non-zero at zero bias. Another process is elastic co-tunneling, where the normal electron is transmitted to the opposite lead via a virtual state in the as a super pair in the superconductor. So again, this process happens within the superconducting coherence link. In this process, the resistance is generally always positive. Again, it happens near zero bias. So the third process, which I need a graphic for, is charge imbalance, where at the interface, quasi-particles are injected into the superconductor and they have a finite length scale. And so this creates a chemical potential and can give you a finite non-local voltage. So charge imbalance, rather than happening near zero bias, it generally happens near critical values. For example, near critical current, critical temperature. So these processes have been observed several places in the literature. Here in particular, is a device, is a gold and aluminum nanowire device. They're injecting current through the normal gold lead into the aluminum superconductor, and they see contributions from all three of these processes essentially. So what we're looking at is lanthanum aluminate strontium titanate. So this is the material where the interface is conducting if the thickness of the lanthanum aluminate is greater than 4 unit cells. And there's a 2-deg at the interface. The 2-deg, I guess 2-del becomes superconducting below 200 millikelvin, and have shown to have a clearance length of about 100 nanometers in 2 dimensions. Now, what we do, which I'll say more about in a moment, is we create superconducting nanostructures, also at critical temperatures of about 200 millikelvin. And the superconductivity in the system is gate tunable both in 2D, which was published in 2008, and also in 1D, which will be discussed by Michelle in session G12.
It was discussed.
So the way that we write the devices is we have a blank canvas, and by applying a positive voltage to a conducting ASM probe and connecting to contacts, we essentially write a nanowire, as can be seen by the increase in conductance when the two contacts are connected. The process is reversible, so by applying a negative voltage, the written structure can be erased. And this provides some flexibility, geometric flexibility, in the types of devices that we can create. So here's one typical device. This is a 5-terminal Hallbar structure. Main channel length of 10 microns is between the two crossings, and typical width is about 10 nanometers. So we look at the local voltage versus current curve. So we're running the current through the main channel between 1 and 4, measuring the voltage at 2 and 3. So this is a true 4-terminal measurement. Here we see superconducting region with a critical current of about 6 nanoamps.
Your labels is 2 to 5 on your y-axis.
And if we go to the so-called non-local configuration, here we're running a current through 3 and 4, measuring the voltage between 2 and 5, and I've just filled in...
Yeah, I guess that's non-local, right?
Yeah. So I just filled in these dotted lines to show where the voltage probes are measuring.
Junction have a size, it might be...
Yeah.
What kind of measure?
It's what?
If the junction have a finite size, you can...
4 terminal?
I mean, you can measure the voltage drop on the junction itself.
Sure.
Yeah.
So, well, anyway.
You know how,
Yeah.
yeah, you could estimate the size, right? Is that what it gave? I mean,
Okay, so
are all of your non-local measurements ones where the voltage leads are touching the current path?
No.
So maybe this is not the one to start with.
So what I want to say here, though, is that here there's a negative resistance below the critical current associated with the superconducting state. But again, this.
But how do you define negative and positive? I mean, why should you say 2 and 5 versus 5 and 2? I mean, I don't know what negative and positive really means.
Yeah, that's hard to do if they don't share like a distinctly like I minus and B minus
Right.
are the same. So I think it's best. Yeah, I'm not sure. I mean, that's an important question.
Yeah, I think this positive versus negative, I'm not sure I would play that up so much.
Okay. Oh yeah, so what I wanted to say here though is that this is a non-local configuration, but it's still within the superconducting coherence, and it's well within the 100 nanometers. And so we can look at other configurations and see similar behavior, but the character changes, the sign of the resistance is changing.
Are those wiggles, all those wiggles are real?
I think so.
I mean, did you do any filtering of the data?
Yeah.
So, is the...
Well, I think this is noise, but...
You mean to show R in the graph?
Yeah. Oh, I forgot to say, when I show the blue curve, what I wanted to say was that this is the derivative of the VI curve up here.
Okay.
The differential versus current. Then we change the configuration and the behavior changes. So not only do we see this within the coherence link, but we also see non-local signals when the current and voltage leads are separated by longer distances. So, and we see this in several devices. In device B here, we're running the current through 5 and 4, measuring the voltage at 6 and 1. And that's the blue curve here, comparing it to the local VI curve. We see it's again associated with superconductivity, but the signal persists for some current above the critical current. This effective separation here is 1.5 microns, which is much greater than the 100 nanometer coherence link that was measured in 2D. In another device, we can source current through 1 and 2, measure at 4 and 3, and again you see a non-local signal.
Why do you choose this particular sign? I mean, what is your choice of what's positive and what's negative?
Here?
Yeah.
This is V plus and this is V minus.
I know, but the point is that suppose you reverse the sign of the current. Would you reverse the sign of the voltage? Because here you have, I mean, the reason I'm saying this is that in the top curve, your non-local signal peaks in the superconducting regime, and in the bottom one, it has a dip.
Yeah.
And then it changes sign, and...
Yeah, I mean, I think this is like a similar issue to what we were saying in the previous slide.
Yeah, I know.
Yeah.
But what I'm saying is that, to me, it seems like it's, if you chose, I'm not sure what you would need to do to choose the convention so that that's positive, but then it would look, the data would at least look similar in the two curves. Because right now, one looks like a mirror image of the other and stretched out.
Right, but that's not exactly unexpected because, well, it's not shocking, I should say, because of this issue of you have cross-Andreev reflection, elastic code tunneling. You'll often have different signs. They have different.
Yeah, but these are the same kinds of devices. So I'm saying the top curve and the bottom curve. Top curve has a peak, and then it changes sign at the critical current. Your bottom one has a dip, and it changes sign basically at the critical current. What I'm saying is that...
Any reason to use the data to define the sign?
Well, But I don't know that you've used any criterion to define the sign. It almost seems random. I can't tell why you chose plus and minus versus minus and plus on your voltage lead.
So what convention?
I don't know.
What other convention?
All I'm saying is that maybe there's some hidden thing, but to me it seems like if you were to redo it, then maybe you could figure out why. But to me, the data looks similar, but inverted. And so I wonder, well, why was it inverted? And I don't know, but I would probably want to look at it in the inverted way so that it looks similar and then try to figure out why, rather than just say, okay, well, because I happen to choose plus and minus, that's the data, and I have to live with this and figure out why there was a sign change.
Yeah, I mean, I spent a lot of time staring at this, and I can't figure out if the data are pointing towards a certain convention. I mean, maybe part of the problem is if there are segments of the wires that are acting like normal leads, we don't know where they are. And so I think that might be one way to define the convention. Because typically what you would do is if you had normal and superconducting junctions, people will typically ground the superconductor, and that's their reference point.
Mm-hmm.
So here we don't know where the reference point would be. As far as we know, the whole thing's superconducting.
Okay, well, I would still recommend swapping that because there's no other reason to do it except that, okay, at least now the data can be looked at and you can see that there's some peak in the signal and there's a sign change that happens near the critical current.
So the same thing if it's well above the critical current, when it's plotted like this, they are the same sign.
Well, I don't know what you mean by well above, because
So
first of all, that's zoomed. No, but look at the scale. Look at the fraction. I mean, to me, I see that signal is actually starting to go down again. For all we know, at 100 nanoamps, it will have crossed sign. To me, it just looks like a stretched out version of an upside down version of the data at the top.
Okay, well, we should talk more about this.
Yeah, but I would say that there's no other reason than I would just swap them and invert the scale.
Also, the unit is the top figure to be like
Okay, so here's the separation between the current and voltage lead. 6 microns, which is again much greater than numerically from 100 nanometers. So this slide needs some work, but if we compare the local resistance to the non-local resistance dependence on the magnetic field, we see that as superconducting state is extinguished at high current, the sign of the non-local resistance changes again. That's what I want to show here. I don't think this slide is done yet.
What is changing sign?
So the non-local resistance here, the way it's plotted right now, these are on different scales. So if you look at 10 nanometers here,
yeah, I think so one thing is that this rainbow scale is not good for, I think you probably want to use something where it's clear to figure out what's positive, what's negative. But here you have so many colors, can't tell. So what I would use like a red, white, and blue scale, for example, or red, black, and blue, or something where positive sign has one color that is very distinct from the negative color, and then it'll be a lot easier to tell what's going on.
Okay, now I can draw this. So now if we look at, this is again device E, we look at the non-local resistance as a function of the backgate. We see that we can tune the magnitude of the non-local resistance. The sign changes with backgating. And comparing this to the local resistance, there's a correlation that we see here. So as the superconducting resistance is compress for higher voltage, the magnitude of the non-local resistance is also reduced. So the paper published in the last year, scanning squid measurements showed imaged the superfluid density in LAOSCO. So this is showing basically that the superconductor is inhomogeneous and it can be tuned with backgate voltage. I need to think more about how to say this. So the question here, as we are seeing these non-local voltages, is we would expect that they would come from normal junctions of normal and superconducting leads, but the way we construct the device, the whole device is superconducting. So it's possible that these signals are coming about because of the fluctuations in the superconductivity. So depending on where we sketch the device, some leads may act more normal than others. Okay, so that's basically what I'm seeing here. Okay, so this may be an explanation for where we come from. So to summarize, we observed.
But does it have to be, or can it just be some, let's say, a spatial variation of the gap? Does it have to be a normal state?
I don't know the answer to that. So it means it has to be a normal state to give a normal signal. I mean, I would think not, because if there's a spatial variation of the gap, then you probably have a smaller critical current in some places, but I don't think we see the critical current vary this much. But
I'm not so sure, how much we should be juxtaposing this 2D thing. First of all, I mean, I'm not sure what they see. Do they see a few little splotches and? First of all, look at this. What's the scale? It's totally different. And
so anyway, maybe we can at least. So we don't know why the signal's here. So maybe we can at least cite this, but not give it so much.
Yes.
And then also say something about the spatial variation of gas. Okay, so here's a summary. We see non-local transport associated with superconductivity. Separation of the current voltages exceeds the 2D coherence length. So these contributions are from cross-under deflection, elastic co-tunneling, and this suggests that there's a much longer coherence length in one dimension versus two dimensions in LAOSCO. And so suggested a possibility to engineer electronic entanglement devices in LAOSCO for quantum information.
I'm Cesaro from University of Pittsburgh. Today talk about the gate non-local transport in gas oxide nanostructure. And when I say gas oxide nanostructure, I particularly refer to the aluminum oxide and the titanium oxide interface. And this is an amazing system because when you put one insulator, which is LAO, on another
another insulator, FEO, we get a conductor interface. And in this conductor interface, we get several novel phenomena, such as high mobility electron gas, metal insulator transition, magnetism, and superconductivity. Even more, recent reports reveal the magnetism and the superconductivity can be coexist in this system. And there's also quantum effect.
Where? Who has seen quantum Hall effect?
I see this one. And John spin orbital interaction. There's more. And I'm going to just focus on several aspects that are related to the space talk. And first of all, the metal insulator transition. There's a 4-unit scale critical thickness of LAO, which below this thickness, we get insulator system, and above this thickness, we get metallic system. And this metal insulator transition can be controlled by the air gate. There's also Jones spin orbit interaction in this system. The magnetoresistance.
You should reference both papers. There's another paper. Well, I know, but when you talk about spin orbit coupling, you should really put both references, even if you're just showing one, because I think they get annoyed because these papers were published back to back.
Okay, so the magnetoresistance measurement shows this anti-localization, and from this curve we can extract the spin orbit coupling strength. And we can see here the spin orbit coupling strength can get as far as large as 10 milli electron volts. And this interface can the superconductivity, like radial current, can also be tuned by the air gate, as well as the spin orbit coupling strength. So I just basically just introduce this system, and the next question will be how we make structures of this system. So basic idea is using the conductive APS cryptography to draw something from the system. Like we can use positive peak voltage to write a wire using electrodes. We can form the conductive jump using these two electrodes. And this can also be reversed, like we use negative peak voltage to erase the wire, for example, the center of the wire, and we can observe the conductance drop. With different peak voltage, we can control the resolution of our writing, and the resolution can go as high as to 2 nanometers. With this technique, we can create different kinds of nanostructures, like the device C, device H, cobalt structure of previous design, and the newest design with device N. We can write a cobalt structure and with this die gate to locally control the structure we write. So the next question will be what amazing result we got on this structure, and this is the non-local transport. And when we say non-local transport in this system, we basically refer to source current in one path and measure voltage on another path which is far away from the current path. Here it's around 10 microns away from the current path. And we found the linear dependence of the voltage and current in device C. And the resistance of non-local transport can get as high as 2.5 kilo ohms.
Yeah, I think you also want to show the local transport, which is what people are normally used to seeing. So there's another graph. I think just because it's, this, I think you want to show that. Also, I would get rid of the exclamation points. So, well, it's good to be. Your voice should convey excitement, but you don't need to put it in the slide, the exclamation point.
And the slide H shows energy non-local signal. And this non-local signal can be controlled by the backgate. Here we show the backgate controls non-local transport. And this non-local transport can also be controlled by the sidegate and similar kind of controllable gate. The non-local resistance can go from 0 to around 225 ohms. Actually, from seeing this data, we can see there seems like a turn-on voltage. So above this turn-on voltage, the non-local resistance is around 0, and below this turn-on voltage, the non-local resistance increase as the sidegate decrease. And this probably related to the current density, which also can be tuned by the sidegate.
Whoa. What is that?
Current density.
57, 58, 59. I don't know what you have there.
Where is it? It's like 1 point. Okay.
Well, okay.
1.57.
Yeah, but that's like 1% or I don't know what's going on there. It's not clear that there's much of a. And where is that being measured? That's going to be measured where at the cross?
Yeah.
Okay. Yeah, I'm not. Yeah. Not sure about that one.
Okay. How do you explain the dip in the middle? Someone asked the virtual something non-local transport, which has been discussed just.
Okay, but you should say that, and you should highlight it and point it out.
Okay. And actually, we are not fully understanding of this non-local transport.
Yeah, but that's not the. I mean, you don't want to write a slide that says needs further understanding. More like needs further work on your part to.
Another kind of non-local figure.
Yeah, I mean, you can just say that there are some devices where, and here you're showing the magnetic field dependence, right?
Yeah.
So, okay, yeah, maybe you can say non-monotonic. Give it a name, something, or yeah.
And even in same sample, we just erase everything and write again, put them together. Quite different kind of non-local signal, which we found is instead of linear dependence, we get this T shape and also the loop shape with the current back and forward. This loop also dependent on the frequency we got the current.
And magnetic fields.
Yes, and when we do magnetic fields, we can see this feature will actually push out.
Yeah, so what? Okay, so you got to break this out into several slides because you're going to show that graph should be a little bit bigger. I think you should show the actual device, not this stick figure device. Show the actual device, and then make the other thing just a full screen. And you're showing you're going to sweep the magnetic field and look at the dependence of the signal. And then you want to focus on certain features and say that maybe the red dot in the middle, this is a superconducting feature, and the other is this thing, changes on a scale of about 6 Tesla. And then you can say, well, we can do gating, and look what happens. I can make it go down, I can make it go up. It's roughly the same feature, but it's changing as a function of the bias that I apply, right? So you want to walk people through it, not just throw everything up and say, needs further understanding, right? So
And actually, we can show this kind of non-local signal by baggage too. You can see here from here. With a high engagement baggage, you can tune the feature to either positive or negative current range. So you need to understand where this non-local signal comes from. Obviously, there's no current flow in the main channel. So how can we match signal on the voltage path? The most possible reason is being current flow in the main channel, and there's several possible theories about this. First is the spin Hall effect, which similar analog to the classical Hall effect. When the electron moves in the electric field, the spin actually feels the force, which is perpendicular to the.
What session are you in?
Oxide.
It's the oxide session.
Oxide session.
You sure?
Oxide and
Why?
Nanowire, non-common session.
It's not oxide.
Nanowire.
Oxide nanowire.
Okay, you need to know what session you're in. It's because the how you give your talk will depend.
The nanotubes and nanowires, then non-carbon, transport and optical phenomena.
Okay, so that's really important to know that. Okay.
And which cause the gain accumulation and the diffusion in the main channel. Okay, and there's also possible helical phase with spin and momentum loss in the system, which makes the spin transport very big.
Yeah, and there you can refer to the Chetan Nayak's paper.
Yeah.
Right. I mean, one thing you know, the spin Halls, like you should dismiss this right away. You should say, well, we know this can't be spin Hall because we don't have, you know, we don't have a polarized source, right? With the one that at least that we are aware of. But maybe the leads are ferromagnetic. Right? You have all this magnetic field dependence and so forth. Okay.
Also could be conducting edge and the soft gas. Similar idea with topological insulator. So actually the current transport through the edge channel get to the voltage path.
Yeah, but okay. Yeah, but what you need to do is you need to say what's problematic with these explanations. Okay. So if it's a 1D wire, it's 10 nanometers, then you could say, well, there could be a lot of coupling between the edges if it's a. Yeah. So it's not clear. And in fact, what I would say is that I would end with the helical phase, which is the candidate that we think is most suitable. And then you don't have to say conducting edges in bulk gap. I mean, you can just say TI phase or topological angle expansion phase, but then you should basically argue also against it. What would lead to something different from that? Okay. I mean, it's possible, but you should definitely at least have one pro and one con.
Okay.
Yeah, but you should have a more description of, let's say, the helical phase. I mean, you could have a diagram, right, showing spin orbit gap and being in that phase, and have a picture of a helical wire. The other thing is that the conductance is the h over e squared, right, which also suggests that it could be a helical phase.
But actually, in gate control, like nothing is not h over e squared. It's like 14 kilo ohm to 10 kilo ohm. The reason I didn't mention it here.
Well, I think what you want to emphasize is that that these wires have a orthogonal resistance that's of order h over e squared, regardless of the length. And we have a graph that summarizes that for several data points. I think it's important to show that there's some reason that even the normal transport is not normal. That there's something unusual about that. But
okay, so the summary of this, introduce the area SPO system and introduce the method we write structure on this system. We also choose the gate non-local transport, which shows the non-local resistance can go as high as 2.5 kilo ohm, and we can control the non-local resistance between 0 and 200 ohm. We can also propose several possible theories. Here's the adapters. Maybe I need to give it to the University of California.
why?
I'm not sure. I'm not sure about the later.
I think
I got this slide from only
I think it's fine, but I mean, well, I mean, the question is, who are your co-authors on the paper, right? But there's no harm in thinking.
Maybe in the 10 minutes talk, I mean, can say the collaboration in the first slide.
Yeah. Yeah. Definitely. Exactly.
and also make the
Yeah, you don't need to do all that.
the acknowledgement maybe also
Yeah.
the first slide.
Like idea. Okay. So I think we made it through. I think it's looking good, and obviously have more work to do, but this is actually the first time we're starting 2 weeks in advance rather than one. I think it's much better. It doesn't feel so.
So when is the next?
We're going to have another one. Well, it'll either be Wednesday, Thursday, or Friday. But I want it to be like the final polished talk. So you shouldn't wait till the last minute and think that, okay, that's just going to be version 2. It should really be working to try and polish these talks so that that's the one that is going to be given. I mean, with maybe some minor refinements.
Is anyone still looking for a ride to get to Baltimore or back?
Yeah, I guess I haven't really figured out my ride.
Okay. Anyone else?